Welcome back to the MATLAB tutorial series. Today, we're exploring one of MATLAB's most powerful capabilities, image processing. You'll learn how to load your own images, adjust pixel values, convert images to grayscale, apply filters, extract edges, and even create animations. By the end, you'll know how to turn MATLAB into a full image manipulation toolkit. Let's begin by loading an image from our computer. In this example, the picture is saved at a specific path. We load it using the imread function. img equals imread, image path, image name, and file extension. Once loaded, the image is stored in MATLAB as a matrix of pixel values. When we open the variable in the variable window, MATLAB shows something like 1227 times 736 times 3 uint 8. Let's break down what that means. 1227 is the number of rows, the height of the image in pixels. 736 is the number of columns, the width of the image in pixels. 3 represents the three color channels, red, green, and blue. uint 8 means each pixel value is stored as an 8-bit unsigned integer, ranging from 0 to 255. So the image is really just a three-dimensional matrix of numbers. Every pixel contains 3 intensity values, one for each color channel. To display the image, we simply use imshow, img. Understanding this structure, that images are just matrices, is essential. It's what allows us to modify brightness, remove colors, apply filters, and perform all the transformations we'll use later in the tutorial. Now, let's adjust the image by manipulating its pixel values. Remember, each pixel is made of 3 numbers, a red value, a green value, and a blue value, each ranging from 0 to 255. When we make the image brighter, MATLAB simply adds a constant to every color channel of every pixel. Brighter equals img plus 50. That means 50 is added to the red value, the green value, and the blue value of every pixel. Increasing all 3 channels makes the entire image appear brighter. To make the image darker, we subtract 50 from all 3 channels. Darker equals img minus 50. MATLAB automatically clips the values so they don't go below 0 or above 255. We can also modify individual color channels. For example, here we eradicate the blue channel by setting all its values to 0. No blue, : 3 equals 0. This affects only the third layer of the image matrix, the blue channel. The result is a dramatic color shift, which demonstrates how flexible pixel manipulation can be once you understand the structure of the image. Color images contain 3 channels, red, green, and blue, so they are stored as a 3D matrix. If we want a simpler representation, we can convert the image to grayscale. Grayscale images contain only 1 intensity value per pixel, so it becomes a 2D matrix instead of 3 layers. Each value represents the brightness of that pixel, with 0 being black and 255 being white. Grayscale images are widely used in computer vision, medical imaging, robotics, and many pre-processing pipelines because they reduce data size while preserving important structure. To compare the results visually, we use subplots. Subplot 1, 2, 1, imshow, image. Subplot 1, 2, 2, imshow, gray image. This allows us to see the original and processed versions together, making differences easy to understand at a glance. Next, let's apply some filters. For smoothing or blurring, we use an averaging filter created with h equals f special average, 7. Then apply it using blurred equals imfilter image h. We can also make edges and textures stand out more using MATLAB's built-in sharpening, sharpen equals imsharpen image. Filters like these are widely used in noise reduction, detail enhancement, and feature extraction. To extract structures from the image, let's detect edges. We first convert the image to grayscale, then apply the Canny edge detector. Edges equals edge of gray image, Canny. This outlines the key shapes and boundaries in the image, a crucial step in object detection, pattern recognition, and many AI applications. Finally, let's animate the image. To create a fade-in effect, we gradually scale the intensity of all pixels by a factor that increases over time. Inside a loop, we update the image like this. Fade image equals uint8, parentheses, double parentheses image, asterisk, k, parentheses. Here's what each step does. Double image converts the image from uint8 to double precision numbers. This is important because uint8 cannot represent fractions. Multiplying by a number like 0.3 or 0.7 would simply round everything to 0. By converting to double, we can safely perform the scaling. Asterisk k multiplies every pixel value by a factor between 0 and 1. When k equals 0, the image is completely black. When k equals 1, the image reaches full brightness. uint8 converts the result back into a normal image format so MATLAB can display it. Displaying each frame with imshow and refreshing it using Draw Now produces a smooth fade-in animation. This technique is useful for transitions, intros, or any visual demonstration where you want gradual change. Before we wrap up, here's a quick tip on how to save any processed image directly from MATLAB using a command. For example, to save the edge-detected image we created earlier, imwrite edges, edgesimage.png. This saves the exact pixel data of the edges image to a PNG file in your current folder. Using imwrite ensures that the image is stored pixel perfect, without any figure resizing or artifacts. You can choose other formats as well, like JPEG or TIFF, depending on your needs. This method works perfectly for saving original images, filtered images, edge maps, or any processed results for later use. In today's video, we learned how to load an image from any custom path, modify pixel brightness and individual color channels, convert a color image into a grayscale 2D matrix, compare results visually using subplots, apply basic smoothing and sharpening filters, detect edges in an image, animate image transformations, and save processed images directly using MATLAB commands like imwrite. Most of what we covered, loading images, displaying them, adjusting pixel values manually, converting to grayscale, using subplots, and saving images, works in any basic MATLAB installation because these features come from MATLAB's core functionality. Some of the more advanced functions like RGB to gray, Gauss Filt, Edge, and other image processing tools belong to the Image Processing Toolbox. If you don't have this toolbox installed, Many steps can still be followed by manipulating pixel matrices directly, since images are fundamentally just numbers. Image processing is a powerful skill in MATLAB, and even with only the built-in tools, you can explore a wide range of visual and analytical techniques. If you enjoyed the tutorial, don't forget to like, comment, and subscribe. Thanks for watching, and I'll see you in the next lesson.